Welcome everybody to Algebra 2, Section 9.2, Adding and Subtracting Rational Expressions. So when adding and subtracting rational expressions, you first have to figure out, do you have common denominators? Here it says like bases on the left-hand side, so I'm going to change that to common denominators. It's not technically incorrect to call it a like base, but I think it can get confusing because really the time that we use the word base in algebra is when we have bases for exponents such as 5 raised to the power 2, where 5 is the base. Or in logarithms, where once again we have like log base 5 of something, maybe 25 equals 2, and 5 would then again be the base in both scenarios. And so that's when we really see bases. And so I think having like bases can be confusing. So we're going to call it common denominators, and unlike bases, I'm going to say without common denominators is what I'm going to call that. So heads up on that. That's just a phrase I think is less confusing to call it just common denominators like we have always. So when we have common denominators already, we actually just skip to step 2, where we combine the numerators and keep the common denominator. And then we're going to simplify this remaining expression just like we did back in section 1, where we reduce vertically after things are combined. So on number 1 here, they already have common denominators as we see, so we can just combine the numerators. So 13a plus 5a is 18a over 4a squared. And then now we're going to simplify that by 2 on the top and bottom, giving us 9 and 2. And then the a's we subtract, and 2 minus 1 is 1, but there's more a's on the top, on the bottom. See the higher exponents on the bottom, so it's a to the first on the bottom, or just a. And so this becomes 9 over 2a. On number 2, we have the same idea here where we are combining these and they have the common denominator 16. When we subtract, though, I'm going to encourage us to change the subtraction to addition, so that way we can then change the sign of everything in the following numerator. So subtract and subtract. It's the same idea of what we've done before when we subtract a quantity or parentheses, and we're going to treat the numerator of the fraction the same way. So now we're going to get 9x minus 7x, which is 2x, and 12 and a negative 2, which gives us 10. All over 16. The reason I like to think of it that way as subtraction as addition and adding negatives is because if we don't, what happens here is we have to then remember I'm doing 9x minus 7x and 12 minus 2. And most often students just forget that we actually do subtracting both of them, so it's easier to do this. Now we're going to see, hey, can we simplify this anymore or at all? And so in order to do that, since there's a binomial on top, anything more than a monomial, we have to look to factor. In this will factor, there's a GCF of 2, and so we get x plus 5 inside the parentheses and a 16 on the bottom. And so the 2 and 16 reduce by 2 to become 1 and 8. And so that leaves us with x plus 5 over 8. Moving on to number 3 here. We have common denominators again, so I'll combine my numerators, and I get y squared plus 10y plus 21 when I combine like terms, all over y squared minus 9. And now I'm going to look to factor this, so just like I did back in section 1, I'm going to encourage you to pause the video and try to factor the numerator and denominator on your own, and then come back and resume the video once you factor those or need some help to see what they end up being. So so continuing now after factoring, the top ends up being in one parenthesis y plus 3 and the other y plus 7. Which parentheses first doesn't matter. On the bottom, since that's the difference of 2 squares, we get y minus 3 in one parenthesis and y plus 3 in the other. Once again, which parenthesis first has no impact on the problem. So y plus 3 and y plus 3 reduce, and so then we're left with y plus 7 over y minus 3. And once again, we can't reduce these y's because that's part of addition, and reducing is dividing. And dividing does not undo addition, it undoes multiplication. Number 4, common denominators again, but we have subtraction. So I'm going to change this to adding a negative. And I'm going to get 1 minus 16a squared over 12a minus 3. And so on the top, when I look to factor that, I'm going to change around the negatives. I'm going to first factor out like a negative 1. And get 16a squared minus 1, because having that variable first makes it more similar or like the denominator there, and that's going to help us in the next step here. So now I'm going to go ahead and factor this. The top is -1 and then 4a minus 1 in one parenthesis and 4a plus 1 in the other. That's the difference of two squares. And the bottom just has a GCF of 3, giving us 4a minus 1. If I didn't factor out that -1 in the previous step and switch around the order there in the signs of the 16a squared and the 1, then these parentheses here would have been 1 plus 4a. Those would swap. And then it'd be 1 minus 4a, the positive negatives would swap in that other parenthesis. And so then as we divide, we'd end up getting a -1 using that shortcut that we talked about in lesson 1. Oh, I forgot my other parenthesis here. So now I'm going to reduce the 4a minus 1 and the 4a minus 1, and I'm going to get -1 times 4a plus 1 all over 3. And as per usual, you're welcome to distribute it in that -1 on the top or leave it as is. And you're also welcome to call it a -3 on the bottom instead of a +3 and have the -1 change that sign as well. That would create the same exact scenario. I just leave it like this, fully factored. On to number 5 here. We're going to say, hey, we have common denominators again. So I'm going to add the opposites there, giving me n squared plus 2n minus 8 all over n squared plus n minus 6. Now I'm going to look to factor, so here's your chance to pause. The top is n minus 2 and n plus 4. Once again, which parenthesis comes first doesn't matter. It's what's on the inside that counts. The bottom is n minus 2 and n plus 3. And so then we notice, hey, those n minus 2's are the same, so those become 1 as we reduce. And we get n plus 4 over n plus 3. On to number 6 here. Common denominators, and we're adding, so I'm not going to change signs, but I combine like terms, and I get 14k squared minus 7k all over 6k squared minus 5k plus 1. And then as I factor here, so chance to pause, the numerator has a GCF of 7k, giving me 2k minus 1. And then the denominator, this is a trinomial, and so it would factor into 2k minus 1 and 3k minus 1. And then there we can see that, hey, the 2k minus 1s are the same, so we can reduce those. And we get 7k on top over 3k minus 1. Now we're going to have no common denominators here, so we're going to have to get common denominators. So that's where step 1 actually comes into play. So we have to rewrite the problem using a common denominator. Then we're going to go through the same process we did on these first 6 problems, where we combine them, combine the numerators, keep the denominator, and then simplify. So here we have to figure out, hey, what's our common denominator between 2x and 3x? Well, they both already have an x, so we don't have to worry about the variable part of it, but we do have to worry about the 2 and the 3. So what's our common denominator between that? Well, 6, and so 6x would be our common denominator. And so we're going to multiply the first fraction. Oh, it just kind of moved me there. We're going to multiply the first fraction by 3 on the top and bottom. You do have to do the top and bottom. And we're going to multiply the second fraction by 2 on the top and bottom to get to 6x. And so that makes it 45 over 6x minus 32 over 6x. And now we actually switch to saying, hey, we're going to add a negative and go through the exact same process we did on the first 6 problems. So 45 minus 32 is just 13 over 6x. And we check to see if that reduces. It doesn't, so we're done. Moving on to example 8 here. We look at our denominators. One is a squared and one is 8a. So to get a common denominator here, our common denominator is going to be 8a squared, because this first one's missing the 8, and the second one's it needs to come up to a squared instead of a for the first. So in order to get this a squared to be 8a squared, we need to multiply by 8 on the top and bottom, giving us 32a over 8a squared. Second one, we're going to have to multiply by a, because a times a would be a to the power 2. You add the exponents there. 1 and 1 give us 2. And so I get 7a over 8a squared. And now once again, I'm actually going to change the sign and subtract, giving me 25a over 8a squared. And I say, hey, can we reduce? And sure enough, you can actually reduce the 25, no, it's not 25 and the a, but the a and the a squared. And so just like we did on the first example for today, we'll subtract 2 minus 1 for the exponents, and that gives us 25 with no a's left on the top over 8a to the first. on the bottom, and because the exponent was bigger on the bottom to start, it stays on the bottom there with the a's, not on the top. So that a became 1, and the a squared became a to the first. And that'd be our answer. On to the back for 8 more examples. Example 9 here. In order to figure out our common denominator, we're going to actually want to look to factor this first. That can make it a lot easier for us since we're going to want to factor it at the end anyway. And so I'm going to factor this, and I'm going to say, oh, there's a GCF, and that's 5 times k minus 2. You're welcome to write that on a new line. Personally, I just like crossing that out and writing it right below. That way I don't have to write a new line. That's my personal preference, but once again, you're more than welcome to write a new line or a new section to where you write actually everything repeated, but just change the denominator. Just do what makes sense to you. And so now as we look at this one has the k minus 2. This one has an additional 5 multiplying where the second one doesn't. So meaning we don't have to change the first fraction at all, but the second fraction does need to multiply on top and bottom by 5. And so this gives us k squared plus 16 over 5 times k minus 2. And the second one is 20 over 5 times k minus 2. And once again, you don't want to distribute on the bottom there because we want it factored out anyway. So now as we combine on the top, I'm going to do plus and negative and get k squared minus 4. Hopefully you're recognizing what that factors as. And we get 5 times k minus 2 on the bottom. And so the top is a difference of 2 squares. And so I'm going to factor that into k minus 2 and k plus 2. And the bottom is 5 times k minus 2. And we can notice, oh, those k minus 2's can reduce with each other. And so those both become 1. And we end up getting k plus 2 over 5. So we have to do a little bit of work to get down to the orange, and then once it was the orange, it's really the same problem as it was last lesson. So it's last lesson, but more now. Number 10 here, to figure out what our common denominator is going to be, we need to factor this bottom right-hand portion of the fraction, so this one right here. So I'm going to go ahead and factor that, so here's a chance to pause. So that factors into y plus 8 and y plus 3 in no particular order, meaning it has the y plus 8, the other one does, but the first fraction needs to get multiplied by y plus 3 on the top and bottom. And on the numerator, you will have to distribute since you'll have to make sure you have like terms and can then add and subtract it with that second fraction, the numerator that. But the bottom, you want to leave it factored. And so technically I should have y plus 3 in parentheses because it's the whole thing multiplying. So the numerator is 7y plus 21 rather, I put 3, over y plus 3 and y plus 8 in no particular order between those factors. And the second fraction is still 35 over y plus, I'm just going to make a match, y plus 3, y plus 8. So because I wrote the first one with y plus 3 first, I'm going to switch and write the second one the same way, just to keep them unified. And so now we can combine like terms on the numerators and get 7y plus 56 over y plus 3 times y plus 8. And then I'm going to look to see if I can reduce after I factor. So the numerator I factor out of 7 and I get y plus 8, which, yeah, that'd be correct, y plus 8. And then we get y plus 3 and y plus 8. I'll second guess myself there, but I had to double check. And so those y plus 8s reduce, and we get 7 over y plus 3 there. All right, now I'm going to go on to number 11 here. Number 11, once again, I'm going to look to factor this bottom left-hand side. The bottom right doesn't need factored. So this becomes x plus 3 and x plus 2. And so I can see, oh, this one's missing the x plus 3, and this one has both. And this one has everything that this one would have. So the common denominator will be x plus 3 times x plus 2. So I'm going to multiply the second fraction by that. So I get x squared minus 5 remaining unchanged over x plus 3 times x plus 2. Second fraction, if I multiply 1 to each of the x plus 3, not equal, but plus, I get 1 times x and 1 times 3, which gives us x plus 3 over x plus 3 times x plus 2. Notice I swapped the order around here to match the first fraction. So you want to match, like I mentioned before. And so now if I actually combine like terms here in the numerators, I get x squared plus x minus 2 over x plus 3 times x plus 2. And so now I need to factor the numerator, so chance to pause. It'll be x plus 2 and x minus 1 over x plus 3 and x plus 2, or multiplied with x plus 2. And so now I can reduce the x plus 2's, and I get x minus 1 over x plus 3. Moving on to 12 here. On 12, could I potentially try to factor this one? Yeah, and it actually does factor, but it's not helpful to us necessarily. Actually, scratch that. It will be helpful to us. So I'll talk about an alternative way to do this problem after we do it the same way we have been. So there'll be an alternative way after the way we've done this for anyone interested. It can save some time potentially. So the bottom left will factor into m minus 2 and m plus 2, which tells us that, hey, this has both factors, where this one just has m minus 2. So to get common denominators, I'll need to multiply this fraction by m plus 2 on the top and bottom. And so now that results in the numerator on the left fraction staying the same. Denominator being m minus 2 and m plus 2. And the numerator on the second fraction changing as we distribute the 2. And we get 2m plus 4. Oop, that should not have been an equal sign. I did that again. There should be a plus sign in the middle. There we go. Over m minus 2 and m plus 2. And so now as I combine, I get m squared plus 7m plus 10 over m minus 2m plus 2. And so now I factor the numerator, and it becomes m plus 5 and m plus 2 over m minus 2 and m plus 2. And so m plus 2 and m plus 2 reduce, and we get m plus 5 over m minus 2 as our answer. Now, I mentioned I was going to show an alternative way to do this problem. Personally, I think it makes my life a lot easier when I do it this way. So let me see if I can find a good place I can do this. Yeah, I'll do it down here. So if I started out with the original problem, I'll just rewrite the original here as m squared plus 5m plus 6 over m squared minus 4 plus 2 over m minus 2. Okay. So the alternative way to do this problem is to factor the denominator like we did, the m minus 2m plus 2, but not only the denominator, also the numerator. The numerator factors into m plus 3 and m plus 2. Now that won't always factor, but it does here. And the reason this ends up being helpful in this scenario, but might not always be, is as I do that, I can actually vertically reduce this fraction. I couldn't cross-reduce because they're adding and not multiplying. You can only cross-reduce when there's multiplication, because that's dividing to undo multiplication. But I can certainly divide to undo the fraction here, to simplify inside of one fraction, a single fraction, not a cross fractions, to undo that multiplication I created. So those become 1. And now as I do that, I end up with this next step where I have m plus 3 over m minus 2 plus 2 over m minus 2. And I notice, look at my denominators. They're common now. They're the same. So I don't have to worry about getting common denominators. I just got them by simplifying rather than multiplying and making it bigger. So I combine like terms and I get m plus 5 over m minus 2, which, guess what, is the exact same answer I got up here with a lot less work. Now that won't always be the case that you can simplify it like this, but if you can, good for you. We actually could have done something similar like that on number 8, which I'll go back and show that real quick. On number 8, for example, I could have started this problem off instead, 4a over a squared minus 7 over 8a. I could reduce these a's, giving me 4 over a over 7 over 8a. So now our common denominator, instead of being 8a squared, is just 8a. So I multiply the left fraction by 8, and the right fraction is good. 32 over 8a minus 7 over 8a. So now I just combine the 32 and the 7, and I get 25 over 8a, which, guess what? Same answer. So it's really a matter of preference and if you catch it or not. But I do want to note on problems like the one we just did on number 12, just because the numerator can factor doesn't mean this will always be helpful. Because for two reasons. One reason is, so even if we factor the numerator, sometimes you still won't be able to reduce it with the denominator because you won't have common factors between the two. And then secondly, even if they do, there's a chance that our result actually still doesn't help us there necessarily. But it can often be the case that it is helpful to look to factor and reduce. And so I personally will always look to factor and reduce the numerators when, like I said, when I can, I do. Number 13, we don't have any problems like that in the future where our numerator can be factored. The rest of these are in the future of this note section, to be clear. That can happen on the homework potentially. It can happen on review and test. But it's like I said, we did the problem originally without doing that, and it worked just fine. Anyway, number 13, nothing to factor here in our denominators, but our denominators are w plus 1 and w minus 7. We can't simply multiply by like -7 here. We have to multiply by w minus 7 because this one doesn't have that factor at all. And so that's going to give us 5w minus 35 on the top when you distribute over w minus 7 and w plus 1. And the second fraction needs to multiply by w plus 1 on the top and bottom because it has the w minus 7, but it doesn't have w plus 1. And so this creates a little bit more work, unfortunately. So we distribute the w plus 1 and the 8, and we get 8w plus 8 over w minus 7 times w plus 1. So notice that shift there that occurred, that we had to multiply by a binomial to both fractions and different binomials to each. So now combining these, I end up getting 13w minus 27 over w minus 7 and w plus 1. And 13w minus 27 just doesn't factor. And so this is as simplified as it gets. Number 14 here. Similar scenario. This has a b, this has a b plus 3, but we can't just multiply this by 3 and get b plus 3. So we have to multiply actually by b plus 3 and multiply these denominators by each other. And we'll get b squared over b times b plus 3 minus 4b plus 12 over b times b plus 3 as I distribute the 4 here to b plus 3. And I should have put that b plus 3 in parentheses. So now I'm going to take this negative and make sure I change the sign of everything in that following numerator. And I get b squared minus 4b minus 12 over b times b plus 3. And at this point, I'm going to look to factor my numerator. So it's b minus 6 and b plus 2. And so I end up having that over b times b plus 3. And even though I was successfully able to factor my numerator, it doesn't simplify. So this is my answer. And if you called the green your answer, that would have ended up being right here because it's equivalent to this orange answer. Once again, I personally have always preferred the factor version because I already wrote it and I had a factor anyway to see if they could reduce. But it's really up to you on that problem where you couldn't reduce. Number 15 here. In order to figure out our common denominators, we're again going to need to factor the bottom on each of these. So this bottom left will factor into 4 times p minus 5. Now I look at that and I immediately notice 4 and 2 can reduce. So even though we can't factor the numerator, we can still have a chance to reduce. Now I'm going to wait to do that for a second to see what this factors into, to see if that'll be helpful or not. Because if I need this 4, because this one already has it, well, I don't want to go ahead and do that yet because I'd be having to undo that work in the moment. This bottom right one factors into p minus 5 and p minus 3 in no particular order. And now I can look at this, okay, well, this 4 is not a part of this. So I'm going to save myself a little bit of trouble by reducing the 4 and 2 and making that 1 and 2. And now as I look at this, okay, I might write a new step to kind of clean this up. Might help a lot of us here as we are learning this. Typically I would do it in this same step personally, but I'm doing this so you guys can learn, so I'm going to clean it up. and just rewrite everything I have after this simplification there that I did. And so now this one is missing the p minus 3. So I'm going to multiply the fraction by p minus 3 on the top and bottom. And that's going to get me p minus 3 on the numerator as I multiply by 1 times 2 times p minus 5 times p minus 3. And my right-hand fraction is missing the 2, so I'm going to multiply by 2 on the right-hand fraction on the top and bottom. And if I didn't reduce in the blue step earlier, from orange to blue, then I would have had to be multiplying this fraction by 4 on the top and bottom here. So I just made my numbers a little bit smaller in this process. So as I multiply by 2 and distribute, I get 2p minus 12 over 2 times p minus 5 times p minus 3. And as I actually combine, I get 3p minus 15 over 2 times p minus 5 times p minus 3. A lot to write there. Now I look to factor my numerator. There's a 3 that's a GCF, and I get p minus 5 left. And I'm already noticing, hey, I'm going to have a common factor in my numerator and denominator, which means I can reduce those. And so that will reduce to 1. And so the top I have 3, the bottom I have 2 times p minus 3. And a reminder, you can't reduce this 3 and this 3 because this is part of a factor, not an entire factor. It's being subtracted by the p, or from the p. On to our last problem of the day, number 16 here. Once again, I need to look to factor the denominators. The bottom left factors with a 2 as a GCF, leaving me with r plus 4. Bottom right has a r as a GCF, leaving me with r plus 4. Nothing I can vertically reduce because I can't reduce diagonally yet with the 2 and 8 or the r and r because these are not multiplying, they are subtracting. So this one I need to have an r in addition to the 2 outside the parenthesis, giving me r squared over 2r times r plus 4. This one over here, it's missing the 2, so it needs to be 2r instead of r. So I multiply the top and bottom by 2, giving me 16 over 2r times r plus 4. And so now as I actually combine these, changing the subtraction to adding the opposite, I get r squared minus 16 in the numerator, and the denominator is 2r times r plus 4. I'm going to go ahead and factor this top of the fraction in the numerator, difference 2 squares, so it's r minus 4 and r plus 4 over 2r times r plus 4. And those r plus 4s can go ahead and reduce, giving me r minus 4 over 2r. And with that, we close out Algebra 2, Section 9.2.